So, stability of complex is what we will take today. Okay, we are discussing coordination compounds, coordination complexes, and so many things we have discussed so far. We have discussed VBT, CFT, okay, color generation, magnetic properties. Okay, so these things we have discussed, and today we will take stability of complexes. Okay, means which are the factor which decides the stability of a coordination sphere specifically, because that is what the complex is. Am I right? So, as we have discussed already that coordination entity or coordination sphere is a unit which behaves as a single entity when it is taken in the complex. Okay. So, how to express the stability of that coordination entity? So, that is what we are going to discuss today. When a complex is formed, then actually what happens in the aqueous solution or in solution of any coordination compound is taken and a specific ligand is added into that. Okay. In that solution, the central metal atom is actually coordinated with the solvent molecules. Okay, and in the process what happens? The solvent molecules are replaced by the particular ligand. Okay, what I want to say is, see, there is an metal atom Mn plus, am I right? So this Mn plus is actually coordinated with, say, if it is an aqueous solution, then what happens? Mn plus H2O, say X. Okay, X is its coordination entity. So this is what is there in its solvent. Okay, if you are taking the central metal atom into its aqueous solution, then this is the condition actually. Now, if you are adding some specific ligands, okay, like L, then what will happen? This ligand will replace these solvent molecules. Okay, say M, okay, M, let us take M as M only, and we are taking N plus minus here. That will be fine, I think. So, what will happen then? Ml H2O X minus 1, because one water molecule is replaced by the ligand. So, this is what is formed, and there will be always an equilibrium between the formed complex and dissociated complex. Am I right? Next step, what will happen? If you will take another molecule of ligand or another moles of ligand, then Ml2 H2O X minus 2. Am I right? Another, third one, ligand, and if you are taking it Ml3 H2O X minus 3. Am I right? So this is what happening in this process, and when all the ligands of all the aqua molecule or water molecules will be replaced by the ligand, then the complex is formed or the coordination sphere is formed. So in this process, okay, how to express the dissociation constant, association constant, not the dissociation, association constant. Association means these ligands molecules are associated with metal atom. So that is why this is formed. Then the adding ligands will associate with this complex, and another complex will be formed. Then the next complex will be formed, and hence the ligand molecules are associating with the central metal atom. Okay. So, for this particular step, the dissociation constant, that is say K1, will be equal to ml H2O x minus 1 upon what? M H2O x concentration of ligand. So this is what is called actually the association constant or stability constant of this step, stability constant of this step. Likewise K2, here will be K2 for this step will be equal to what? M L2 H2O x minus 2 upon M L H2O x minus 1 L. Am I right? This is what the dissociation constant or stability constant for the next step, second step. Likewise K3 will be equal to Ml3 H2O x minus 3 upon Ml2 H2O x minus 2 L. Alright. So this is what the stability constant for the third step. Okay. So these all constant actually are called stepwise stability constant. Stepwise stability constant. Okay. Say the final step is like n number of ligands you are taking. Okay. Then what you will get? M L X. Okay. The final one is formed, say N1. So you are taking N1 ligands and you are getting the final coordination sphere. Okay. So this is the final product of this reaction. Am I right? So what we can do is, say if you are having M, okay, H2O X n plus minus, okay, whatever it is, or it will be actually plus only because we are taking a neutral one. So okay, plus only. If you are taking another ligand like anionic ligand, then of course maybe negative as well. So if you are taking this metal ion in its aqueous solution and taking all the X ligands all together, then what we can see, the reaction is happening in one step and MlX n plus, am I right? So this is happening in a single step. So the stability constant for this step will be, say, beta. Beta will be equal to what? Beta will be equal to M H2O X. Am I right? Sorry. MLX, not H2OX, because the product is MLX n plus upon M H2O X and L raised power x, of course, and x number of ligands if you are taking, then of course what will be the stability constant? Okay, that is beta is equal to MLX upon M H2OX L raised power x. So this is the stability constant for the formation of an MLX. Okay, because the reaction we are considering in a single step, So that is why the formation of this coordination sphere or coordination entity or complex is called the overall stability constant. This is overall stability constant beta, am I right? Overall stability constant. So overall stability constant beta is equal to mlx raised power n upon ms2ox L raised power x. This S2O sometime you may take, or if you don't want, then you may also skip this water molecules or solvent molecules. Okay, you can put the simple reaction like M plus L is in equilibrium with ML. Okay. Now the next step you can put another M, then ML2, okay, N plus. Likewise you can take L3, then M, L3 and so on. So this is also okay. There you will take just M and ligand, metal and ligand. So because most of the metal ions are taken in their respective solvent, okay, then only the reaction will happen, of course, because we have to take them in any solvent. Like if you are taking here, okay, we have seen that if you are taking NiCl3 in water, okay, in the previous video we have taken that if you are taking NiCl3 in water, then what we will get? We will get this one, NiH2O 6. Okay, this is what we got there, and thereafter we add ethylene diamine. Am I right? So the ethylene diamine replaced these water molecules. So that step by step we added ethylene diamine and we got the different colors. Am I right? So this is what actually the reaction is. Okay. For convenience, okay, we can take just metal atom or metal ion and take the ligands. Okay. But actually this is what happens. So this is overall stability constant, and this is observed that the overall stability constant beta is equal to the multiplication of the stepwise stability constant. Okay, means K1, K2, K3 and so on Kn. So overall stability constant is equal to the multiplication of or the product of the stepwise stability constant, and the stability of a particular coordination sphere or coordination entity or coordination complex depends upon the value of this beta and the value of this stepwise stability constant. Stepwise stability constant decreases in the next step because the ligands are crowding the central metal atom. So if you will compare K1, then it will be greater than K2, K2 will be greater than K3 and so on greater than Kn. So that you also take care. The stability constant decreases with steps. Why? Because the crowding increases or the charge decreases on central metal atom, and that is why the stability stability constant decreases. Okay, so this is actually the overall stability constant, and more the value of this overall stability constant, more will be the stability of the complex. Why? Because in that case the concentration, that equilibrium will be shifted towards RHS. Okay, there is always equilibrium. Okay, for saying we just say that coordination entity behaves just an entity in the solution, but that is not the case actually. Okay, some extent of that coordination sphere or coordination entity also dissociates. Okay, so it depends upon value of this mln x n plus upon this one stability constant. More the value, more will be the stability of the complex. Am I right? So that you take care of, and like that I told you, the value of a stepwise stability constant decreases with the steps. Am I right? And the reverse, if you take like m l x n plus, okay, in a solution, okay, then what you will see, m, okay, m plus x l. Am I right? M plus x l means the coordination sphere getting dissociated. Okay, so it means the stability, if you want to express the stability in terms of instability constant, in terms of instability, because this is the reverse reaction of this one. Am I right? This is reverse of this one. So what will happen then, if you will take like ki means instability constant. Now what we will say, instability. Why? Because now we are dissociating our complex. So that is why instability constant, because we are considering here the stability of this coordination entity, and now we are going to dissociate it in this reaction. Okay, because reverse of the formation is dissociation. So ki will be equal to what? M, am I right? Like H2O you are taking. So M H2O, let me take the full reaction. M H2O X N plus X ligands. So what we will get, M H2O X raised power N L power X upon what? M L X. So this is what is called instability constant. What? Instability constant, and we can see this is just reverse of stability constant. So beta is equal to 1 by ki. The stability constant and instability constant are reverse to each other. So this is how, on the basis of stability constant and overall stability constant, we can decide the stability of our complexes. Okay, there are two kinds of stability we can discuss for the complexes. One is called thermodynamic stability. What? Thermodynamic. So thermodynamic stability, and another one is kinetic stability. Kinetic stability. Okay, so what does it mean actually? If you are taking a particular complex like say a complex, and we are getting product. Okay, so for this reaction actually plus heat of reaction delta H. Am I right? And what we need for this reaction? Activation energy. Okay, because before activation energy we cannot get this reaction. So now on behalf of this heat of reaction or enthalpy of reaction, the stability is called thermodynamic stability. What? The stability is called thermodynamic stability. Okay, on the basis of this activation energy, the stability is called kinetic stability. Means EA will tell you how fast the reaction is going to happen. Okay, delta H will tell you whether the reaction is endothermic or exothermic. If delta H is like say positive, then unstable. What we will say? Unstable. If it is negative, then what we will say? Stable. Okay. Likewise, if EA is more, then what we will say, inert complex, and if it is less, what we will say, labile complex. So this is thermodynamically more, this is kinetically more stable, this is kinetically less stable. Okay, this is thermodynamically stable, this is thermodynamically less stable or unstable. Okay, so this is how we can classify our stability as well into two categories. One is thermodynamic stability and another one is kinetic stability. Thermodynamic stability depends upon heat of reaction or enthalpy of reaction, while kinetic stability depends upon energy of activation or activation energy. So that you take care of. Okay. So now the factors affecting stability. Okay, factors affecting stability. So factors affecting stabilities, there are so many factors which can affect our stability of our complexes. One is the charge on central metal atom. More the charge, more will be stability, because if the charge is more, the ligands will approach closer to the central metal atom and more stronger will be the coordination bond or the bond between central metal atom and ligand. Okay. Then the another factor, ligand field. Okay, strong ligand field generally makes stable complexes as compared to weak field ligands. Okay, so that you can also take. If you consider charge and if you consider the M2 plus, then the scientist, there are two scientists, Irving William. Okay, there is scientist Irving William. So they have given a series for the stability of Mn, manganese 2 plus, then iron 2 plus. Okay, this is the order, I think. Then cobalt 2 plus, then nickel 2 plus, then copper 2 plus, and then Zn 2 plus. Okay, so this is the stability of the 2 plus ions of the first transition series. Okay, whether irrespective of ligands, whichever the ligands is, the stability will be same for these ions. Okay, these transition metals. So this series is called actually Irving-William series. Okay, Irving-William series. Okay, if you consider the same type of ions like double positive ions, then irrespective of ligands, the stability of their complexes will be following this order. Okay, so this is Irving-William series. Then nature of ligands. Okay, we have seen that effect of multidentate, chelate formation, because we have already discussed that if the cyclic structure, specifically the 5 and 6 membered ring, 5 membered ring is the most stable ring when chelates are formed. So if chelates are formed in the same oxidation number with the same metal atom, then as compared to monodentate ligand, the stability of chelate will be more, because that symmetry and cycle matters, you know. So that is another factor. And then the stability of various complexes play an important role in analytic chemistry. Okay, this is importance actually. We use so many coordination compounds for analytic purposes. Okay, like separation of copper and cadmium. It is difficult to separate copper and cadmium, but using the coordination compounds we can separate copper and cadmium as well. So that is another use of actually use of. So I think that's all about stability of complexes we have discussed, and for the day it is enough, I think. Thank you very much for watching. Have a nice day.